Well, good morning. I'm just upgrading my machine to the latest build of Windows, to the Redstone 2 build. So while I was doing that, I thought I would just quickly start recording some of the SWR video that I was asked to record. So I'm not going to go in and spend time explaining what standing wave ratio is. There are far smarter and far better presentations of this than I could give that are on the net. So I'll link some of those in to it. And especially there's the classic AT&T Labs, Bell Labs video, I think it is. It's phenomenal. It is a great example. We'll put that in there and you'll be able to go in and find that. And I recommend watching it, even if you know what SWR is. It's just a classic example of old educational films. Anyway, to go through it, what we're going to take a look at today are a bunch of these components here. The primary things that you'll use to measure SWR. Well, let me step back. Let me start over here. What I have here is I have two loads. This is a 909A from Hewlett-Packard. This is going to be a very low SWR load, especially at the frequencies we're going to use in this kit. This is just a crappy 50 ohm terminator that I've got with a little connector. I wanted something that would give us a little bit of a better value that would be easier to find. So grabbing this and putting this together, let me go across to my vector network analyzer, which is my 8714C, and measure the SWR for this device at the frequency that we're going to use, which is 1 gigahertz. So if we look here, you'll see that the SWR for this is 1.236. So knowing, and the VNA is a very accurate way of doing this. You have a calibration kit, you set it up so that it knows and it can get rid of all the errors that exist in the chain, so it really is only measuring this one thing. So we know what that is. We'll take a look at the crystal detector and how you would use that in this case here. And then we'll utilize two of these 84A power sensors. And we'll be doing that as part of a return loss measurement. Now, when I say return loss, what I basically mean is when you send the power, if we look here at let me zoom this in, because this actually does make a reasonable teaching aid, a reasonable sort of drawing here. Basically, what we're getting is, with the SWR and the return loss, is that we're sending power down to the device under test, and there's some amount of that power that gets reflected back and would come back up the cable here, and that causes your standing wave ratio between up and down your line. But you can also measure it simply as the power that's coming in or is incident on the device under test, and the reflection power, and the difference between the two of those is fundamentally the return loss. It's how much of the signal is lost coming back to the return, and you can go back and get a number that may get very large very quickly, especially when you have very well matched loads, because effectively when the loads are matched, there is no return loss. So there's no return, so you would have a massive amount of the return loss effectively in the comparison between the two values. So based on that, what we're going to go do is we're going to go use these devices here, and we'll use this little short to take a look at it. And these devices will help tell us what the return loss is. Now, this is listed as an SWR bridge, and an SWR bridge, or a directional coupler or a dual directional coupler in this particular case, all basically do the same thing here. What you're going to get is, in this particular case here, this is just a cheap Chinese bridge that I got off eBay. This has about a 10 dB loss of power. So coming into here, you're going to get about 10 dB down, and then you'll get whatever the reflected value is here. These bridges should be balanced, resistive bridges, and there are many articles on this, and effectively, for a true SWR bridge, you should be putting a modulated signal in at a known volt, that comes in, and then the voltage that you're going to get out, and then modulation is usually around 1 kilohertz or something like that, and then you're going to get a reflected modulated voltage, or a reflected modulated signal at 1 kilohertz that has a voltage that is the proxy for the SWR, and then a properly calibrated meter would enable you to go and read that. Really what you're getting here is basically that difference between input power and reflected power. These directional couplers, these are very cheap. You can go get these. Are they accurate? Well, we'll take a look. These items here, and here I have two different versions of this. The first one here is a 778D, and this is 100 megahertz to 2 gigahertz. And these are a micro strip line, I think the term is. Basically, if you go and have a look, I did a video on this that showed the layout of it. But basically, there are two strip lines. There's a line that travels through here and goes through the instrument and on a substrate. And then there are lines that come down here and from here to here. And each of these two items here are 50 ohm loads. And so these, I believe they're 50 ohm loads. These things, this microstrip line is then going to be, because of the layout together, it's going to effectively be coupled back and forwards. And so what you'll get is, if you put 10 dBm through here, you should get roughly 10 dBm out the end there. I think there's I'd have to go have a look at the thing. Okay, so I don't know if you can see that. I went and pulled up the calibration report on this guy, and so at 1 gigahertz we're going to have a 0.32 dB drop. So as that signal comes through here, if you put 10 through here, you'll get 9.68 or something out. So the aim of these things is to have very little impact on that through thing. But then there'll be about a 20 dB coupling between each of the two ends. And what does that mean? Well, that means that if you had all of the power flow down here and then measured the reflected power, you'd basically be 20 dB down on whatever the reflected power is, and you'd be 20 dB down up here. Now, why did they do this sort of dual approach? Well, what you can do is you can measure the power here and you can measure the power here, and this is telling me what the actual input power is, and then this is telling me what the reflected power is. Now, when I measure here, if I'm putting 10 dBm in here, because of this 20 dB mean coupling, I should be measuring minus 10 dBm here. Now, that, if the signal was perfectly reflected, should be the same. Remember that we'll have 0.32 of a loss, and then the reflection won't be perfect. But in an ideal world, that would mean the same thing here. So in a perfect, 100% return loss case, both of these things should measure the same. So that makes it very, very easy for you to go and measure return loss using a bridge like this, or a directional coupler. This is a 2 gigahertz to 18 gigahertz directional coupler. You can actually get these 11692Ds are actually on eBay fairly cheaply. They are the other one, the next, there's a replacement part which is in this model range, which is the 772D, and they're very expensive. These, I saw in the low hundreds. I think the reason for this is that the test port here is an APC7 port, and so to really use this properly, you have to have a metrology grade APC7 adapter to ensure that the reflections you're getting are minimized in the coupler here, in minimizing the coupling to your device under test. but you can get one of those and then get this up to 18 gig range. Now we'll be doing our testing at 1 gigahertz, so we don't need to use this guy. We can just use these two guys here. Now the last piece of kit that I wanted to show you is this guy over here. Let me move my coffee out of the way. It's morning while I'm waiting for the machine to take the build from overnight. Let it boot, and it's looked like he's getting very close. The last thing that we're going to show is this guy here, which is a HP 415E SWR meter, and we'll show how this was used to measure SWR. Now, I'm not going to show how you would measure SWR utilizing this directly, because to do that you need a slotted line. And there is a link to a YouTube video that I have, and again I'll put that down in the notes, that shows a university lab utilizing one of the slotted lines. But that's what the SWR on this is set up to do, is to take a slotted line measurement on the unit. Instead, what we're going to do is we're going to do return loss again, but we'll use this as the measurement tool instead of using these guys here, and we'll just show how you would do that and work that out. Alright, so that's all of the kit here. Let me get this guy set up, and then we'll measure some SWR, or some return loss as the case may be. Alright, so here we are, we've set up now. We have the SWR bridge, we have a signal coming in from my signal generator, and we have an 84A power sensor. So what we're able to measure is the power that's going to be reflected from this point here. So let's go and start my measurement here. And so this is not a perfect bridge. There's some loss in this, and as we go through this, we have to be cognizant of the fact that these power sensors haven't been calibrated completely. So there is going to be some error in this. But if we get within a few hundredths of an SWR ratio to where all of the readings agree, I'll sort of declare that victory. So here we are. We have minus in, but let's put in what you're supposed to do is to set this up is to have a short, so you're getting 100% reflection from there. So now what we're losing is just all of the implicit losses in here. So this is minus 23.76. So let's put that into the calculator, and then we're going to measure our device here now. So let's take that out. Let's drop this in. Alright, so now we're measuring minus 43.35, so let's put that into the calculator. 43.37. Alright, and so now that gives us 19.61. Now there is a formula that we could go in and calculate that, or you can grab one of these cool charts, and it's a mini circuits here does this chart, and it basically enables you to look everything up. So 19.61 is going to be between 1.24 and 1.23. So it's when we looked at our signal generator, our vector network analyzer, we saw that it came in at 1.236. So that's a pretty good reading for a cheap device like this to come and get us the SWR of this device. Let's go take a look at doing this with a dual directional coupler. Alright, so here we are with the dual directional coupler setup, and you can see that we have the input signal here, we have a power sensor on the incident wave, and we have power sensor on the reflected wave, and then we have the test port down here. So let's just take an initial reading of the power coming in, and we see that we're getting minus 30 dBm. Now, one of the cool things with using these directional couplers is that I don't need to, you saw when we used this guy, that we had to take a measurement, decouple things, put stuff on, reset things up, and then we could get the second measurement to get our SWR. Now, we don't need to do this with this fully directional coupler here, dual directional coupler, because I can get both measurements at once. So let's run this again. And now what we're doing is we're going to pick up the individual values. Now, we talked about where we having the reflected signal coming straight back, and you can see that we're getting 30 in here, we're getting reading 31.3 down here. So that's giving us an SWR of 28.96, which is very high, which is basically telling us that all the signal's reflecting back. And what I can do is I can take this little short here, put this on, and we should get a bit more coming back, because now we're seeing that the return loss is only 0.22 dB. And so the SWR that we're reading is 72, which is exceptionally high. Now, if we had a very well matched load like this 909A, I can drop that on, and you'll see that the return, let me get that put on. You'll see that we should get very close to, what we're actually getting here is a very low return loss coming out of the end here. So, we're now reading a return loss of 26 dB, which is an SWR of 1.1. As these become more and more accurately the match between the load and the rest of the transmission line, that SWR approaches 1, because you're getting, in a perfect case, all of the power would be absorbed by the load and none of it would be reflected back. So given that, let's go and put our test device on, and when we screw that in, you'll see that we're reading a return loss of around 18.9, which, if we again look here, we had 1.236, we're reading 1.255, so we're within 2/100ths there. That's a pretty good match for reading that value. Now, the equation to do this is actually not that complex. Let me just grab my pen. What we're going to do to from the return loss to go and work out the SWR. The SWR is basically going to be 1 plus 10, the return loss on 20 over 1 minus, I think this is right, return loss over 20, and that whole equation is basically going to give you the SWR value here. So I'm calculating it in the app automatically, but it's really not that hard to calculate if you were going to go do it directly from the readings, instead of using the table. The tables, though, are really good. They're really quick, and more importantly, because they're set up around the return loss, you could just simply take that measurement minus 18.97. That should be 18.97, but for the purpose of this table, and then 18.97 we come up here, we're between 125 126. So that's not too, that's pretty good, pretty happy with that. We're a little few errors in here. Part of the reason this is a little less accurate than the other one is not because of the directional couple. The directional couple is very good. The problem is in my sensors that the calibration data on this, while it tells me what the calibration factor is for 1 gig, I don't know how accurate it is because I haven't sent these away to be calibrated yet. This guy's got one of these horrible little point chart thingies on it where basically there's a little graph and somebody sticks a hot pin through the graph to create a hole, and that measures, is roughly where it is, rather than the printed values that you can see here. When I send them away to be calibrated, I'm going to get printed values, so hopefully that will make this a little bit more accurate. Anyway, that's how you do it with a dual directional coupler. Let's take a look and see how we would do it utilizing the crystal detector. Alright, so here we set up. What I have is I have the signal right now just coming directly into my Riggle here. So let's actually just get some data about this. The probe is going to need to be 1. Let's turn on measure. We want the hardware counter. Let's go channel 1 there. Let's measure the VPP, and let's set the can actually set the font size. Alright, to extra large. There we go. So we're measuring, this is basically a 0 dBm signal. So we're roughly in the ballpark there. It should be like 223 or something. Anyway, we're seeing it's 100 megahertz. So this is sort of what you would get out of here. And the question you would ask is, like, why would I bother measuring this 1 kilohertz modulated signal on top of this, when I could just simply go and look at the signal directly? Well, the reason that these came around was that the frequency output and capability of these signal generators drastically outstripped the capability for you to view the signal directly. And so as the frequency increases, the inability of the test gear that people had to go and look directly at the signal meant they had to come up with ways to look at it. And so what they did is things like creating these crystal detectors, where what I'm actually doing is I could put in 18 gigahertz signal into this, and then at the other end take a 1 kilohertz modulation out of it, and I can see that and look at that modulation on my scope here, and then use that as a proxy to understand what the signal is. So here we are at 100 megahertz. If I took the signal up to 1 gigahertz, you see that effectively the bandwidth limitation on my scope, take that signal away. That's fairly standard. Everyone, sort of understands that. What I can do is take this out of here. Let me just connect the crystal detector in. And plug this back in here. Now, you'll see that we've jumped up. So what we're now getting is DC voltage, and that DC voltage is proportional to the power that's coming into the crystal detector. And that should be consistent, so if we step this in a bit, you'll see that we're very close to 2 graticals up. If I now take that to, well, if I take 10 gig, we're probably going to drop down. If I take it to say 3 gigahertz, we're now sticking back up there. So 10 was a little much for the cable and the connectors and everything. So, what I was able to do is to be able to look at a signal that's much higher than bandwidth of the gear that I've got there. Now, what I'm going to do is come back to 1 gigahertz, and I'm going to turn on some AM modulation. And now, what we should be able to do is to come back in, and we're going to see a square wave come through. And that is basically, I'm feeding an amplitude modulation into the signal, and I'm modulating it with a square wave. And that square wave is coming through this system, being detected. The amplitude of the crystal detector is giving me that square wave there. And so now, what I can do is I can do things like looking at how that square wave changes based on the reflections and things for frequencies that are well beyond my test gear here. So let's take this out. Let's drop this back in, and we'll use this guy again because it's nice and small. And we'll plug our crystal detector into here. Now, if you remember, we're getting a 10 dB loss here, so we have to sort of step this up a little bit. And let's get the trigger back in here. And now you can see that, let's see if I can, we're going to clean it up a little bit. Now you can see the square wave still through there, and I can read the voltage on that. And I could, you know, if I put this guy in here, you know, you'll see that, you know, that's what I'm now reading with my short. You know, I could take that, the voltage there, then I could drop this guy on, and you'll see that the voltage drops right down. And that's another part of the problem that we have, is that now, you know, if I go in and I can't get enough resolution on my device here to read that that value. So while it solved some of the initial problems, there was other things that needed to be done, and that was where the 415E came in. So let's drop that in place. All right, so here's our 415E, and you know, I talked up front of the video about how these things would normally be used as a direct SWR meter, and what you would normally use is a slotted line. And I'll add a video in somewhere, I hope, that will show you the slotted line, you know, give you an idea of how the slotted line works, and a link to it below. But when you do that with the slotted line, that lets you use the SWR values here. Let me grab my little pointer. The SWR scale directly, and what you would do is, because effectively what the slotted line is basically a way for you to get a probe in, and the waves propagate through the space of the slotted line. So it's basically just a line, you know, a cylinder with a hole cut down the side, and then your crystal detector slides along that slotted line, and you're trying to find the peaks, because with the standing wave ratio, it's where all the waves combine and subtract. So you want to find the maximum peak and then the minimum peak. And what you do is, with this to do the SWR, is once you've set that up, you set up the gain here to find the maximum. I think it's maximum. You do the maximum first, so you'll get a maximum reading here, and then you go and find your minimum. And as you work through to find the minimum, you'll be able to read the SWR directly off the thing. And it may be the other way around. You know, it's been 30 odd years since I used a slotted line, and I didn't buy one. They're a couple of $100, and I have no real use for it. So that's how you do it. Check out the video. But what I've got here is, you can also use this as simply as a return loss meter. That's effectively what it lets you measure in here. And so I have the crystal, you know, I have the crystal connected here, and this runs through this cable into the input here. And we have it set for high because these are high impedance crystals. You know, if you've got a low impedance crystal, like less than 200 ohms, you're going to set it to low. And then you could also use bolometers, which are effectively doing that same, you know, how much does it take to heat something up and so on. But I have crystals. So what we're going to use this is basically as a return loss meter. So I have the system set up, and it's putting out, you know, about 0 dBm. And so we should be reading a voltage here. So if we start, you know, coming through and raising the gain, you'll see that we're not really getting any, you're starting to see a little bit of gain there. We're not getting anything, and the reason being is that this is a tuned amplifier. So this frequency thing here is it's looking for 1 kilohertz, and you can tune this back and forwards to peak your value here as that becomes the, you know, the filters here are aligned with the signal that you're inputting. So let me turn the signal on here, and now we can go through and find where we start to see, and you can see that we started to get a little bit there, and now, you know, we've got a bit more. So now I can turn the gain up a bit, and we want to get and have this at about 0. So that's, camera's right in the way, hang on. Alright, so there we go. So that's 0. And what I've got is I've got my short on here. So we're now set up. And so if we take this off, and you can see the return loss changes, and now I put this on, we're going to drop down again. And so what I'm going to go do now is I'm going to step this up by 10 dB, and you know, we're up a little bit. So let me come in now, and what we can do is this part, this reddish part here, enables you to take this bottom dB scale and then segment it across the top here and expand effectively the range. So remember, we added 10 dB, so we're, you know, minus 10 from where we set with our short. So now let's go into the expand, and I'm going to want to expand range 8 there. So now if we read across the top, you know, we're at 1.1, and that was 8. So that's going to be, so that would be 8, that would be 9, that would be 10. You know, so if we come back here and look at this in norm, you can see that we're just around 9 on the dB item there. And so when we come into 8 here, we're at 9.1. So that shows that the return loss that we're getting here is around 19.1 dB. And so if we come in here and have a look at, you know, 19.1, we're between 1.25, 1.24, and that equates pretty well with, you know, what we measured in our vector network analyzer. Now, I could, if I had this bridge, or I put in my dual directional coupler or so on, you know, this bridge could be rated to, you know, 30, 40, you know, gig, and I could still be measuring using, you know, this gear here and this crystal detector, well, this up to 18, the crystal detector, and with the proper lines and everything like that, and getting a good value of SWR. And I don't need to have an expensive oscilloscope or so on that would enable me to do that. So there you go. That's a walkthrough of several different ways to go and calculate SWR and view it. I hope you found this interesting, and we'll catch you later.